Okay, so hopefully you've had some time to think about this a little bit, try to determine what types of graphs, connected graphs, would have an Euler path or an Euler circuit. And maybe you found that it has to do with how many edges you have coming out of the different vertices. So in particular, on this graph right here, we had an Euler path but not an Euler circuit. And any Euler path you could come up with would have to start at this bottom vertex and end at the other bottom vertex, or vice versa. So the only paths you had were determined to start and end at those vertices. And so what's special about those vertices? What did we notice about those vertices? Well, suggestively here I've written a definition, which is the degree of the vertices. So the degree of a particular vertex V is just the number of edges connecting V to another vertex. So for this vertex right here, the number of edges coming out of it, that's the degree of that vertex. This vertex has 1, 2, 3 edges coming out of it. So I'm going to label this with its degree, which is 3. Similarly, down here we have 3. And in the center we have 4 edges coming out, so this is degree 4. Up here, 1, 2, 3, 4. This is degree 2. This is degree 4. I'm going to go through and do that with all of my graphs here and see what do they have in common. So in this middle graph, the degrees are 3 all along the outside and 4 in the middle. In this graph here, we have 2 on the outers, then 1, 2, 3, 4 on the inner square, and 4 in the center. And in my last graph, I have 4 here, 3 here. 1, 2, 3, 4. 2, 1, 2, 3, 4, 5. 4 and 2. Oh. I see now that I did mess up here. All right, and I'll show you why in just a second. So the graph that has an Euler circuit, you'll notice all of the degrees are even. And this kind of makes sense because to have an Euler circuit, you need to be able to start at one vertex, visit every edge, and come back to that starting vertex, right? So you need to leave, and then you need to come back in again. Or if you started here, you would need to leave, come back in again, leave, come back in again, right? To start and end at the same vertex. This graph here at the beginning that has an Euler path but not a circuit, most of its vertices had even degree, except for the starting and end point, which had odd degree. And that makes sense because this has degree 3, which means if you were to start here, you would leave out of one of the edges. At some point you would have to come back in through a second edge, and finally you would need to leave again from your third edge. You'd never be able to get back to that point, right? And similarly over here, at some point you'd have to come in, then go back out again, and then come in again, and you wouldn't be able to leave at that point. So those two odd degree vertices means you could start at one, end at the other, and visit every other edge. Now, in this graph that had neither, we had 1, 2, 3, 4. We had 4 odd degree vertices. That's going to be a problem because if we were to start at one of them, you would leave, come back in, leave again, and then you'd never be able to visit this one again. But that's true about this vertex and this vertex and this vertex as well. So if you have more than 2 odd degree vertices, you're not going to be able to find an Euler path. So now I see why I made a mistake in this last one, right? So here we have 1, 2. We have exactly 2 odd degree vertices. So this suggests to us that it's like this first graph here. So maybe I should have just tried to start at one of the odd degree vertices. Maybe I just did it wrong. So I'm going to try it again in pink. Let's go up, over, down, over, let's go to the middle, back to this corner, out again. Then we could try to go up, up, down, and then over to the triangle and back over here again. So it is possible. We just have to start at this odd degree vertex and end at this odd degree vertex. So this does have an Euler path, right? So that was my mistake. And it has an Euler path because it has exactly 2 odd degree vertices. So that's what the Euler path theorem tells us. It tells us that if you're looking at a connected graph, it's going to have an Euler circuit if and only if the degree of every vertex is even, And it's going to have an Euler path without an Euler circuit if there's exactly 2 vertices of odd degree. This is a great theorem. This is really useful. We can use it for any connected graph to test relatively quickly whether it has an Euler path or an Euler circuit. Okay, and so if we think back to that graph that we drew for the Königsberg problem, it looked like this. Now if I were to go through and find the degree of each vertex, there's 1, 2, 3 edges coming out here, 3 edges coming out here, 1, 2, 3, 4, 5 here, and 3 here. Clearly, the degree of every vertex is not even, so it's not going to have an Euler circuit. And there's more than 2 vertices of odd degree. All 4 of them are odd degree. So since there are more than 2 vertices of odd degree, we can conclude by this Euler path theorem that this graph has no Euler path or circuit. Okay.